LEDs possess a little bit of magic to me. I was born with the Edison light bulb. When LEDs came along, I turned my ears, each one turned, to keep up with it. Here's something I made at home. It's a clear piece of plexiglass. I didn't have it engraved. My wife gave me some color beads, which I glued them in. If you'll unplug that just for a second, and I get enough light, you can tell the beads have some color. And the reason I did that is my QSL card looks like this. It's got sort of a color spectrum, if you will, and it turned out pretty decent. So I have 2 blue, 2 green, 2 yellow, 2 amber, 2 red, and you can buy these little wall warts. You've heard of these before, wall warts? Mm-hmm. Some people call them power transformers or adapters, but women don't like them. I'm sorry, ma'am. You have a nice living room wall and you plug this little black thing in the wall and it just destroys your nice drapes and decoration. That's why we in the field call them wall warts. They do look like something that I have growing on my forehead here. I'm going to turn this off now and want to show that to you. And then I'm going to go over here and if I can, show you some picture, a couple quickies, and we're going to get to it quickly. 10 millimeters are this size, 3 millimeters are this size. That's obviously 2 or 1 millimeter, if you will. These look like they're in Christmas tree lamp holders. When you buy new Christmas tree lights, try not to buy incandescent, unless you so choose. This ad was in the newspaper, and it caught my attention. Energizer is the same as Ever-Ready. So this is an Ever-Ready product, if you will. But what caught my attention was this LED light employs a light fusion technology. Boy, that caught my eye. I had to know more about it, so that's what I went and did. So if you will, I'm going to get out of here and get into what. Remember I mentioned in the very beginning that, well, I'll let my slides do most of the talking. Here we go. I hope you can read that. I'll sort of fill you in. 600 years BC, there was a Greek mathematician, a philosopher, astronomer. His name was Thales. I don't know anyone named Thales. That's an unusual name for me, Thales. He said that you pick up this piece of amber and you rub it with silk, somehow it'll pick up, get little tiny sparks after dark, and it seems to have magical power because it attracts little pieces of fluff and straw, paper. They had paper in those days. By the way, the Greek word for amber is electron, spelt with a K, but if you look, that's where we get our words electricity, electron, and so forth. Those Greeks were pretty clever. The Greeks were known for their Roman numerals. I was a 1, B a 5, X a 10. Go ahead and answer. If you say, well, what's L mean?
50.
50, and C?
100.
Is 100. People ask me my age, and I tell them I'm 0.8 century. Most people don't know how old I am. But my wife knows I'm 88. But really, I'm 88.2 now. My birthday was in October. No lunch for that. Okay, why didn't these Greeks discover binary? Anybody know what? This is an old story. If you know, raise your hand and don't. Good. I got something different. I'm pleased with myself. Here we go. There's why they didn't invent binary. They never came up with a symbol for 0. What is binary? 0 and 1. That's it. And I feel sorry for those fellows. They were knocking on the door and just missed it by so much. There's a fellow named Arthur C. Clarke. He writes science fiction. He's deceased now. He's from England, British and so forth. He said, any sufficient advanced technology, something we don't understand, something we can't figure out, we think it's indistinguishable from magic, hocus pocus. Clarke was a very good fellow. He was one of the first people to suggest, why don't you put a satellite in orbit Guess what they name it now? The Clark belt. That's how we do business. Amps come from ampere, volts came from volta, right? I haven't heard of any Parkers lately. I sometimes think I never had the original thought all my life. That's embarrassing. Let's continue if I can. This fellow here also is a science fiction person, and he said the world is full of magical things. They're just waiting for us to find out and get smarter, get sharper. Like I mentioned a while ago, color light-emitting diodes were available for decades. Additional decades passed before a white light-emitting diode appeared. The length seemed unexplainable. Why so long? That's why I'm here tonight. That captured my fancy. Even Energizer advertises LED fusion technology. And that LED fusion introduced W8DMR, me, to confusion. Boy, was I confused. I didn't know the difference between fusion and fission. I thought it was just misspelling half the time. That's not true. So, as you see me roll along here, I'll try to help explain things. I'm going to explain some of that magic, okay? But before I do this, you need to help me review my arithmetic. Being 88, I've been out of school too damn long. I do a lot of self-education. I survive that way, but it's good if you take a course every so often. So if you don't mind, I'm going to do this. I'm going to make the assumption that you're dumb like I am. What does SI stand for? There's some type of units, they call them SI units, and I would like to discuss these units. You can forget that SI, it's just what a whole lot of people, basically the world, agreed to use. And here's the units they chose. Forget SI for the moment. What you want to remember is this magic word here, exponential. Before I go into here, I want to show what an exponential is. This is a man's definition or a woman's definition. By definition, any number, any doggone number, even pi, any number raised to the 0 power equals 1. Let me show you. Here's any number, and if you raise it to the 0 power, by man's choice, it's defined as 1. Thank good he did it that way, or the system wouldn't be worth a darn. Oh, I got it. 10e. Oh, I got it. 10 is this base right here. The e stands for exponent, and son of a gun, there's the power 0. That's why this is unity. It's 1. Could that be made just a little bit more clear? 10 to the e, 10e0. Uh-oh. How come some are in blue and some are in green? 10e0. Oh, there it is. I try not to cheat on these slides. If you find something, tell me. I need to change it. Here we go. 10 to the 0 power. Why, 10's a number. Any number, well, it should be 1. Oh, I got it. Here's an example. 10. Oh, that points to the exponent. I got it. E is for exponent. And you go to the -3. That's milli. That's 1/1000th. Oh, I got it. And these numbers are getting larger, but the value is getting smaller. Over here, the numbers are getting larger, 10 to the 18th. Can you picture a number, like a digit 1 and 18 zeros behind it? How would you like to write that over and over? Suppose you're trying to do something and you don't have much printing space, and now you start using it for 18 zeros in a row. Can you imagine? 10e to the +99? That's a lot of zeros. That's hard for me to appreciate. So here we go. Let's do one more. Repeat, if you will. E is for exponent.
E is for exponent.
10 is the decimal base. And the -3 is the power to which 10 is raised. Oh, but there's something else up here. Maybe you didn't notice it, so I put this in just for my benefit, not yours. Quantity is greater than unity. Okay, quantity is larger than unity. Start with a... Oh, that's right. All these have capital letters. That way, if you ever see one of these, you know it's bigger than 1. But if you look over here, they're all lowercase, and I'll be darned. Quantities less than 1 start with lowercase. Here's an example of what I'm trying to talk about. In electronics, there's something called Boltzmann's constant. Little k is what we use for that symbol. This k is for Kelvin, degrees temperature. This k is a constant. And it's all those zeros, 138 joules, that's a form of energy, Jk. How would you like to have to write that over and over if you only had 1/4 of an inch or 1/2 an inch at the margin of your note paper? Why not do it this way? K, this little k right here, is equal to, oh, I got it, 1.38. I can handle 1.38, that's like 1 1/3 joules per Kelvin. And there it is, 23 zeros. I count them very carefully. Over to the decimal point is 23, right here. Hey, that's a pretty good system. This exponential thing, well, why, Bill, did you take my time tonight and show me this? I didn't drive out in the cool, just for fun, using these SI units, System International. Yes, sir, it takes less print space. Arithmetic is simplified. Your eye doesn't have to work as hard. And if you're going to work with cosmic or atomic magnitudes that use quantities like these, they're much easier to accommodate. Let's move on, it's getting dark outside. Oh, first of all, I planned to open with this slide tonight, but I'm a little tardy, a little late, but so be it. Don, is this the right place and time?
Yes, it is.
Am I in the right place?
Mm-hmm.
This is the right group? I got
made
1
it.
point so far. Boy, did I have trouble finding it after dark. I've never been to London, Ohio before, that I can recall.
Congratulations.
And light-emitting diodes. Well, I must do this. I shouldn't, but I'm going to do it. I'll come back to this. We've covered that. We've covered that. We may have time to cover them all, but I'll skip what I think is boring, or you may tell me. Let's do number 3, if we may. Oh, I got it. I see why you spent time. You had to set people up so that, well, let's see how those work. A typical living virus is 1/10,000,000th. Oh, that's how I went to school, I learned 1/10,000,000th. That's the English system. This is System International. Oh, I got it. This fellow is 10 to the minus, that number is the same as this number. I got it right there, look at it. A virus, a living virus, I hope I don't get one tonight, is 10 to the minus 7. I got it. 1, 2, 3, 4, 5, 6, 7. If you want to call it one virus, you put a decimal point right there. You notice I'm shaking a little bit, but I hope that'll go away. Well, what's this molecule? Remember I mentioned cosmic things or atomic things. The exponents are great. You know what? Since these all have 10, you'll notice later on, most people don't write 10 anymore. They make the assumption it's powers of 10. Yes, watch out, you get into logarithms, it'll be a different kind of a system. You have to be smart enough to see the difference. They usually use a lowercase e over there when they do that. Okay, which is the larger, this one or this one? Well, that's larger. It's only got 7 places. This one is 9 places. Well, this sucker over here, this little boy is 100 times, 10 to the minus 2 is 100. Minus 2, that's 100. What's these little green guys? I'm going to go over and find out. Why, it's an atom over here. An atom is 10 times smaller. Well, this should be one number smaller than that number. It is. Uh-oh. What's inside of an atom? Well, they have like a nucleus. Inside that nucleus, look at this. From here over to here is 10 to the 4th. That's 10,000. Remember, 10 to the 2 is 100. 10 to the 1 is only 10. You'll be doing this better than I am. Inside of here, there's little things. What's inside? Why, there's protons and maybe some electrons, not in the nucleus, but there'll be some neutrons. They also hide over here. And, oh, this is only 1/10 smaller than that. Uh-oh, here we go. A quark is 1,000. Well, we're down to 10 to the minus 18. They gave this a name. They found something even smaller. They call it Higgs boson. What else is after the Higgs boson? How many times can you keep cutting something in half? Forever, until you get to minus infinity, and that's a long trip, infinity. Notice how I cheated? All my symbols aren't to scale. If I had to make this thing in scale, to do it really scale, I'd be out of business. The little dots in the projector, then the computer, the resolution, I can't do this to scale, so I had to fake it, if you will. Relative size in the good old SI units. I'd like to get the heck out of here and see what's next. I think it's time to apply something of this because I have something more important to talk about than this, believe it or not. Did I ever get smart when I started fooling with this guy? I didn't learn this in school. Hydrogen is the simplest and lightest. Why? Well, it only has one proton and one electron. And you know what this electron is doing? It's going around here like this. That didn't impress me one bit. What impressed me was this. It says, I'm going to be going this many times a second. 1 times 10 to the... This baby is really moving. Now, why does this circumference have to be exactly one wavelength? A wavelength is a cycle. Why does this thing have to, if you will, cycle around here exactly one wavelength? If it was a tiny bit more than one wavelength, it would go like this. If it was a slightly bit less, it'd go like this. It'd auger in or it'd auger away. For that helium atom to be helium, it has to work like this, or it wouldn't be helium. I didn't know that when I started to learn about LEDs. Oh boy, let's see. I'm going to skip the mass up here. This is more important. Oh, I got some arrows here to show you it really is doing this. Well, how fast is it? What's the meters per second? It's fun to measure in feet, but we use 12 and 36. But if you stay metric, it's tens and thousands and hundreds. Someday maybe our whole country will become metric, become part of the SI system someday. Here we go. If this is -1 charge, and this is +1 charge, I made those charges up. The charge is really this. Look at that. There was a fellow named Coulomb. He was the guy that came up with this idea and did a lot of work. And how could they salute him? They put his name on what he discovered. 1 times boy, these have, by the way, down here, Bill Parker says the net charge of the atom is 0. Because if I've got a -E, and it's that charge, and this thing is going to keep going like this, then that force has to remain the same attraction force. That force has to remain the same. And look what it says. -1, and you take a +1 and add them together. Take a +1 and a -1. Uh-oh, the net charge, almost all atoms, except radioactive atoms, are 0 net charge. That's okay. I'd like to show you one more thing. It may happen before I get to it. Oh, I got it. This guy here has to have that same charge. 95, except for less than 1%, 0.5%, this whole atom is nothing but air. So is silver. So is copper. What I'm talking about here is so tiny, if you try to dust it in your hand, there's nothing there. It's really hard to tear these apart. Here we go. If we could take what's that? Oh, by the way, one single proton, that is the nucleus. This is the only atom that has a single proton and has a nucleus. Check this out. If I could get 1 cubic centimeter, and tonight, if I can find it in this box of silliness, I have a little bag of 1/4 centimeters, and I'll use this light just to help you see it a little bit. That little white, that's 1 cubic centimeter. A centimeter by the time, okay? If I had something that big, and it was all composed of those protons. The nucleus density is 200 billion. What's a billion? 10 to the plus 6, right? Pounds per, wow. If I had one of those here right now, you might be following me toward the center of the earth. The cement might not be enough. The earth might not be packed firm enough. You might be chasing me. You may do that before I finish tonight anyway. Okay, I think I've shot that one. Is there anything left to talk about that? I hope not. Oh, there is something left. There's always something when I'm here. These two guys have an attraction or it wouldn't stay there. And that attraction, Newton, turn it into pound. Pretend it's ounces. You don't have to know what a Newton is. But this force is very tiny, but it's still 8.2 times 10 to the minus 8. That's like 1 over 100,000. Here we go. Excuse me, I get the right button. Gravity. Gravity is 3.7 E. Oh, look, they're getting brave now. They've left the 10s out here. They get more room by skipping this 10 out here all the time. When you pick up a book, they don't tell you this. You have to be smart enough to figure it out. Since this, I got it. Gravity is this strong, but the force between here is this much. Let's see, this is minus 8. This is very small. Minus 47 versus minus 8. This gravity is 8 to the 39th. 39 zeros, and hang a 1 if you will. Weaker. This has got more force than what gravity has. Therefore, when you work with atomics, you can ignore gravity. Gravity doesn't affect these atoms. Isn't that sneaky? I didn't know that either. Wow. Well, I've got to move on here. I think I'm going to do this next. Yeah, let's try this one next if we can. If you see one you like a lot, tell me. I'll play it. You say, Bill, I want to see number 7 right now. I got to go home. Tell me. Here we go. I need to get up once in a while. By the way, the number of electrons in the rings, that is the atomic number. If you go, the atomic number of helium is 1. It has 1 electron. 2, guess what 2 is? Helium. 2 electrons, 2 protons, okay? I'll quit with that. This, according to what if you read ahead of me, I'll appreciate it. Read ahead of me if you'd like. In succession. First there's 2, there's 8, and there's 4. Start at the inner ring and work towards the outer ring. 2. What's this? Yeah, that's the nucleus. 2 on the first ring. 8. The outer ring has just got 4. Is that important? Boy, is that important. You won't believe it. But I'm going to show you why that's important. All to help you understand how these little LEDs work on fusion. There's more to an LED than meets the eye. That's okay. Let's go on, Bill. It's getting dark out. There we go. What's inside this nucleus? Remember I said all atoms are net charge is 0? If this has got 14 electrons, there better be 14 positives because the silicon atom net charge has to be 0. You can figure these out ahead of me, I guarantee it. Inside is 4 fellows that have no charge. If you take an electron and you take it away, if I were to reach up here and want to pull that electron away, say I could do that. So these atomic physicists are so smart, they make up the rules as they go. What I just said is they learn something new every day and they got to cover their tracks carefully. So I have some books at home that have leather, sort of fake leather on the back with gold printing. There was nothing but electron flow. Nothing but electron flow. That's when I went to school. Down here I have books that are no longer, they have fine colored glossy paper on the outside and they're shiny, really. Hole flow. All those books are about hole flow. So what's this hole routine? Well, I brought something with me tonight. I brought an electron. And with all this LED stuff, there must be something here I could grab that would produce more light than I want. Let's try this. And here's This is one of the very inexpensive, I didn't use the word cheap. This is a very inexpensive Radio Shack flashlight. I took the regular incandescent bulb out and put something like this in. Oh, that looks like lunar light, LED. Here we go. Here's this electron. See this electron right there? There it is. If you take that electron away, I'm going to do that right before your eyes. Oh, this is not the scale again, right? Okay. I hope you can see this in the dim light. I just took it away. What did it leave? And thank you. Hey, go. Will you? What do you charge? Anyway, there it is. It says hole plus charge. Oh, if I take an electron away, thank you, it's going to leave a hole, and that hole is going to represent what a proton's doing. That's how the physicists covered their butt, pardon my expression. I kept that electron up there to go away. But first, bookkeeping, more bookkeeping. 14 and 14 says 0. Removing an electron needs a hole, but I haven't left the hole yet. I want to get that hole out of there, get the hole out of here. That's why my wife says, get the hole out of here, husband. So, example, here we go. I'm going to sit back down on blocking. Example, just remove just one electron. Let's see what happens. Observe what happens. There it is. I want to remove that electron sometime today. There it goes. Oh, boy. Hey, ooh, wow. And what did it leave? Oh, I got why you made these ping pong balls. I got why you made this now, Bill. I understand now. Hey, there's a +1 there and a -1 over here. And those fellows want to go together. I have no glue, no paper. Look at that. Yes, I put a couple of magnets in here. My wife said, aren't you too old to be doing things like this? And I said, just started. Well, let's see. I think there's some more words after this. I don't waste the screen. You notice I use every square inch. Uh-oh, look what it says. This atom used to have a net charge of 0. But now, 14 and -30, uh-oh, this atom looks like it's +1. And this atom says, I'll get you if I can. You give me the right circumstances, I'll capture you. And believe it or not, that has something to do with LEDs, but it's tricky. I've got to prepare you for something. You're not going to like me after this one, but maybe you will. Oh boy. I'm going to ask questions now. I want to hear an answer. I tend to put this away from time to time. Well, I like this one, it's better. Somewhat. Here we go. Remember those Roman numerals that I tried to make fun of in my own humble way? That's a Roman numeral 3. Why didn't you put a regular 3 up there? Because it's too confusing. But boy, did it confuse me years ago. 3, 4, 5 Roman numerals. This is, all 3s fit in this row. All 4s fit in this row. All 5s fit in this row. What's it say over here? This group number, I used the word group 3 times. This is the number, the quantity, the number of electrons in the atom's outer ring. Oh, prove it to me. We'll talk about this if we have time. Here I go. I'm going to select my old buddy, hydrogen. Boy, it better come over here and say 1. If it doesn't, I'm going to quit. I'm going to go home. I lucked out. It's hydrogen. The symbol is H. Atomic number is 1 because it has 1 electron in its only ring. That number is 1 because of him. Yes, and it's in group 1. It's over here someplace. Group 1, 2, I didn't have room. And what's this? Oh, it says number of electrons in each ring. 1 ring, 1 electron. Simplest. I want to see what helium looks like. Helium is, they put hydrogen in balloons. They also put helium in. What's the symbol for helium? You have to start reading these. I don't have time. And it has 2 of them. And it's good. Oh, that's the number. And 2 in the first ring. That's right. A while ago on that silicon atom, there was 2 in the first ring, 8 in the next ring, and 4 in the third ring. I wonder what the heck I'm going to do something. I'm going to type in 14. Is 14, is that going to be the number for silicon? Let's see if oh, look how easy this is. Anybody can master this. 14 is the atomic number. Group 4, hey, there's silicon under group 4. Oh, I got it. All these have got 3 in this, over here in the last ring. All these over here have 4. These fellows have 5 in the last ring, whatever ring it happens to be. I got a 2, 8, and 4. And what is silicon? Well, we use that for semiconductor purposes. We make diodes out of them. Uh-oh, light-emitting diode. I'm starting to sneak up on this fellow. He talks too much. By the way, all these green fellows, they use those in what they call a germanium diode. They call them a germanium diode. And these fellows, they use those in what we call a silicon diode. So I just, I quit. Let's see. I hit the wrong button. I'm going to try one more. If you ever think about metal, what about this metal? Oh boy. It used to be $1,800 an ounce, but what is it now? About $1,100? Something like that. It's an excellent conductor. But what do you notice? Look what you notice. This gold has 6 rings. Do you suppose that's why it weighs so much? I don't know. Here we go. Oh, it goes 2, 8. Most of them have, I got the first ring will take 2, but no more. Second ring takes 8, but no more. But look at 3 and 4. Oh, this progression is found throughout all the elements on this planet. Not all the elements, but this progression in the element that supports it, okay. But look out here. Look how, ring 1, 2, 3, 4, 8. Here we go. Out here in the 6th ring is one little electron. That electron is not being held very tightly. It's not grabbed by its neck. Excuse me, I just got these and they don't fit well. That's the truth. That's my fault, not yours. And if you laugh, I can handle it. This electron is held so loosely that when you put a little potential, electric energy, you take and put a little energy on gold, it says, you can use my electrons to carry that current wherever you want right now. No wonder gold has the lowest resistance. No fair working on things below absolute zero and things like that. I'm talking at room temperature, if you will. If I were to look at like tin or copper, let's see if I can figure out what copper might be. I'm going to try copper. I don't remember all these real well. Well, I didn't pick copper, did I? Let's try another one. I'll try one more time maybe, and then call it quits. Well, look at iron. Iron's got only 2 in this ring. These are held a lot tighter than what they're held in gold because it's in a closer ring. I'm ready to go on now. You got the feeling for this. Okay, why did you bother to put these up here? Well, I'm going to come back to this in just a minute. Well, let's do a 31. What does 31 have it? It says I better be gallium. I better be gallium, and I am. And I have that, only 3 out here. Let's do silicon. We know what that one is already. Yeah, it's got 4. Let's do germanium. Did you know germanium diodes take less energy than what silicon diodes do? Why? Well, notice it's got more rings. If I can get this guy, I'm missing my buttons here. It says, the 3 out here and silicon, the 3 are held much tighter than what germanium holds it in 32, because it's farther away and out there. So it says that you can borrow those 4 with less energy. I'll do one more. Let's do antimony. Let's do a 51. Here we go. Something wrong?
I think she has a question over you.
Got a question?
Yeah.
I'll come over to you. My hearing isn't as good as when I was younger, your age.
With gallium, why are there 2, 1 positive and 1 negative?
Will somebody repeat that question, please? A little louder for this old man.
With gallium, why is there
Look,
1 positive?
hang on. You're special.
Okay.
a while back, there's a little lump up here now. And if I take a transistor radio and turn it up full volume and tune off the station and hold it about right, not over here, but right about here, every second you hear something going click, click, click. I now have a pacemaker. Not only do I have a pacemaker, but now I have to do things like this in order to hear. And it takes about 3 seconds before it goes honk. Did you hear that? It's real soft. Try again, man.
With gallium, why is there one positive and one negative?
Why is there one positive and one negative?
Yeah.
I'm not sure that God knows. It's the way this did you hear that again? Real weak? Okay. Now I can communicate with you. You have a good question. It's my hearing is not this poor. Why is one negative? Why is one positive? Well, let me express it this way. I'm going to ask you a question. If you have two magnets, and there's a north pole on one end, on the other end of the south pole, and if you put two norths together, they don't want to touch. But if you put a north and a south, they click together. A while ago when I held the green and blue together and they stuck, north-south were happy. That's why there's plus and minus are electrons. In a world of atomic theory, plus charge, minus charge. Okay? By the way, two pluses say no. I'm going to show that in just a moment. Two minuses say no, but opposites click. That's that attraction I've been talking about. Good question. Now, I'm going to do a 51, and you had a good question. And this is the last one on here for a while. And it's, oh, look at that. Oh, I got it. Why is that 5? Well, it's in this column where there's nothing but 5. 6, 7, 8, whatever. Whatever the atomic table will have. I thought there were just like 75 elements. No. They're up to something like 190 elements now. But some of these elements are only there for a fraction of a microsecond. They're gone. You can't pick them up out in the desert, no way, or on the beach. But they gave them a name and found them. Guess what name that hung on number 99? Einsteinium. He got his collection, didn't he? He got his attention. He earned it. Okay, I'm going to say goodbye to this chart. What shall I do that? I ask for nothing, and then I press for nothing. That whole ball of stuff was right there. How do you make PN material? P for positive, N for negative, young lady, hear that? PN material. How can you make PN material? Wow. When I make a mistake, I do that. Here we go. Oh, I brought one of those with me tonight. I'm going to bring it over to the young lady. Silicon. I should do this right now. Here's my wife gave me these styrofoam balls. She's into crafts and hobby and sews and things like that. So I cut them in half. She says, "You ruined them." I said, "Yes, ma'am." Anyway, in the center are 2, 8, and 4. Remember that silicon jobby? It had 2 in the center, 8 and 4. You fellas sitting out there, you seniors like me, she'll remember that a lot longer than you'll remember my talk tonight, because I know something you don't. It's fading all the time as the battery is weakening little by little. Are you ready? See the 2 in the center, the 8 and the 4? If you hook these fellows together like I'm going to show in a moment, you can make, these are all silicons. I have 5 silicon atoms here, if you will. There's a name for this, but I'm not ready for it. You might be. Okay. Notice here's number 1. Around it is the 4th. And if I use this, it might be better for all of this. Here's the one I'm talking about. It's in the center, right up here. And around it are 4 others. I know that's a flat, one-dimensional display. I can't help it. But catch what happens. This electron right here, minus for electron, is shared with this atom. And this one over here is shared. Oh, I got it. I see what's referred to as a covalent pair bonding. Covalent pair bonding. These electrons that can be part of another atom are called covalent. These curved lines, I think, are sort of dumb. I think it'd be much smarter to teach people if you took these same 5 atoms. Notice I put a little asterisk in each one to show you, okay, those 5 atoms bond together as a molecule and form a silicon crystal. Something you can sell by the pound. Why not just put a little dash over here, show a dash, and let it represent 2 of those lines? There would be if I was doing this the first time for beginners, I think I would use this symbology and throw that symbology away. I want to modify this silicon atom crystal. You have to learn to read up here. 4 adjacent atoms share 1 electron. Share, 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 share. What would happen though if I would take something from group 5? Remember group 5 had 5 electrons in the outer ring. Antimony. Let's see, covalent pair bonding, yes, but I have 1 more electron that no place to go. Here's an electron that I call a free electron. It's not free, but it's available to be used. I can donate this electron to do other things, and we gave that a name. Since electron is negative, we call this type of material, silicon with antimony added, a donor electron. Let's go one more. You went you're over in that chart again, where there's only 3 electrons in the outer ring, 3 covalent, 3 bonds, but not enough left for a bond. There's not a pair of bonds here. There's a hole left here. And this hole says, you give me an electron, and man, I'm ready to do business. I'll become a crystal for you if you'll give me an electron here. Okay? And all this, what was I talking about? How do we manufacture NPN positive negative material? By adding certain impurities. Let me get clear on this covalent thing. It's sometimes confusing, particularly for young people. Here's atom number 1, atom number 2, green, blue. Here are 2 electrons in this atom's outer ring. This one is in this outer orbit, and this one is in, I got it. This one here is bonding. This electron, that is covalent. These outer ring covalent electrons aid in forming molecules to make a crystal like I showed you over here. Okay. How about this one? It's only in this ring here. It's not in this ring. Therefore, it's not shared. It doesn't count. It's not covalent. You can say it's valent, but it's not co. Electrons are held to the nucleus by electrical forces between them. Sort of like a north-south magnet. That's what the word covalence means. Boy, I'm just flipping right along here. I think it's time for some entertainment. I consider this entertainment. You engineers are all alike. Well, how many people remember what number goes there? Any number with an exponent of 0 is 1, right? Hey, that's 1 hertz. Remember cycles per second? To make it simpler, we pick hertz, right? Hertz are now cycles. I still think cycles up here when I see hertz. But I gotta say hertz. That's 10,000. That's 100 million. Oh boy, look at these fellows. Here's one over here, 10 to the 20th. Long wave, radio, AM, broadcasting, short wave, microwaves, millimeter waves, nano. That should be a lowercase up here. I goofed. That's a mistake. That should be a lowercase nano to follow the system, okay? I hope I don't change that and get home now. Okay, what do we have down here? Well, 1 over the frequency is wavelength. There it is. That's 100. Boy, if you have 1 hertz of frequency, a wavelength is going to be 100,000 meters long. No wonder we don't transmit as hams on one meter band. I don't have a backyard near that size. Okay, Here, look, uh-oh, if you go up in frequency, higher and higher in frequency, look what the wavelength does. Oh, wow. Did you know that this line I have up here is way out of, that line should be so small, none of you can see it. If that line was to scale, it'd be invisible. But I put it up here so we can see it. I'm going to say, well, what's on this side? I'm going to say IR is there, infrared, ultraviolet is over here, and I brought this line down in order to get this in the middle of my projector. I said, well, I'll just come over and show, so it doesn't turn that corner there. I put the corner. Okay, but, oh, you mean red, violet, orange, yellow, green, blue? Yeah, from this hertz to this hertz. And what these hertzes? Look at these hertzes. 10 to the plus 12. You mean light is like a frequency, and it operates that many times per second? 10 to the minus 12? That's a lot. The unit is tera. Hey, I got it right here, didn't I? Look, see, I got it right, lowercase. I paid attention to what I preach. Okay. From 400 to 700. Notice if frequency goes up, as frequency gets higher, the wavelength is less. The lower frequency has a longer wavelength in nanometers, 10 to the minus 9. Well, for years and years, they wouldn't accept that light was a frequency, and they wouldn't accept it was a particle. And then finally, they explained it, they had to use both frequency and particles to tell the truth. That took a long time. There were a decade or two, several, before scientists would agree on that to get along. Okay, I thought you'd find that interesting. What I showed you that is so I could do the next one. Oh, I couple them together. I don't have to punch it again. Let's see. Skip that. That doesn't mean anything. Color, wavelength, and frequency. Here is, once again, the wavelength, if you will, IR, UV. And down here is 700. I put some cycles there, and I put some cycles over here. Oh, the visible spectrum is from here to here. Frequency in terahertz. Why did you put this whole chart here? Well, I want to cover color. In order to make an LED that lights red, it takes 3 elements. Gallium, arsenide, and nitrogen or nitride, if you will. Gallium, phosphor, okay. And something else that I didn't know. In order to get these, the fellow that developed these and made them, the people, the engineers, they had to employ isotopes. I didn't know what an isotope was, so I haven't learned what an isotope was. But I learned it took 3 different things with isotopes involved, 3 different situations, that many situations to get those colors. Magenta, orange, yellow, 1, green, blue, 1, 2, and 3, whatever. Okay. Well, what is fusion? It's a combination. You combine something into a single. Well, I want to combine 2 singles at a molecular level. I don't want to take sand and cement or sand and gravel, whatever. I want to use something on an atomic level, fusion. Suppose I have element A and element B, and I want to combine them into a new element, different name. I wish to, on an atomic level, take these atomic devices, combine them together, and I like to make A and B into one, which you can't separate unless you work hard. There it is. A and B are gone now. You don't get to play with the sand and the gravel separately. You get to play with C only, unless you're willing to do what? Apply fission. Fission is separating. Oh, okay. Fusion is combining. Fission is separating. That you have to remember. I can't do that for you. Each part of a complete element. A spontaneous, with this atomic stuff, you don't do it putt-wise. A spontaneous division producing elements, I want to see that. Oh, you're going to start with Z? What's inside of Z? I didn't know that A and B are in here. Oh, you're going to use X and Y. Okay. Well, I want to take those guys and separate them, and there they are, X and Y. Z is gone forever. We now have this and this. Chocolate and vanilla. Let's apply this to LEDs. And if you want to go home, tell me, I'll speed up. I'm looking for my keys here. There we go. LED fusion, a recombination, a combining of holes and electrons. Oh yeah, there's a natural attraction and we just want to combine those. And that's how an LED works? How does that make light? I don't understand, Parker. Promoting an instantaneous energy release in the form of electromagnetic. Oh, I want to see that. I want to see that. And if you do this right, you can generate colors by something called stimulation. And I cautioned you, it's best analyzed in accepting that wave and light is wave and particle duality. Light has a duality of those two fellows. Oh, I got it. There's that hole you talked about. Yeah, you took an electron away and it left a hole. That's spooky. And oh, there's the electron, but wait a minute. You modified that electron. Details later. Here's the hole. Here's the, by the way, that's my symbol for this enhanced electron. EV stands for electron volt. You don't have to know that. Just pretend that's an electron. But the plus says I've enhanced it some way. I have an enhanced electron volt. Well, look, if you read ahead of me, look. H is a positive charged hole. And this EV is an enhanced charged electron. There's the electron. The plus is the enhancement. Now, I'm going to ask that. I want to fuse them together. Here I go. It won't last long. It's going to go buzz, buzz, click, whir. There they are. I wish to combine those two fellows. You don't show the plus. There's a reason. There's a reason the plus is not shown. Why? During this fusion up here, the hole will accept the electron. This is the secret of an LED being told to you tonight. When this electron goes back to the hole in the atom says, I only have house, a room. I accept only the charge of an unenhanced electron. Oh, I got it. When these two guys right here went together, the H and the E says, combined, no net charge. Well, what happened to this plus over here? Well, I showed it as a V here. I'll run this again. And the V is that enhanced energy from the enhanced electron, and it comes out in the form of electromagnetic radiation. Here we go. The charge the atom rejects. This is what the atom would not accept. The atom will take this and it'll take a minus E, but it won't accept this fellow. That energy instantaneously, not put, instant. I can't say it fast enough. Okay, that's what takes place. When that takes place, and here's the secret of an LED in words if you're listening. And recombination, and combining those, and recombination of H and E only, electron only, enhanced charge release is EMR. This enhanced part is dumped out in a form of light. What's another name for light? Young lady, do you happen to know by chance, either one of you over here, what another name for light is? What unit does the light have? That's all right. You're not supposed to know. I guess so. What?
Volt.
A bullet. He's not a bit. I can say again.
A volt.
A volt? No, it's not necessarily a volt. I didn't know either. It took me a while. But guess what name they gave a unit of light as a particle?
Photon.
I heard somebody say photon.
Yeah.
My hearing aid isn't very good. But take credit. You get 2 flashlights tonight, not just one. Okay. I appreciate that. Okay. You're not used to me, I can tell. I'm not used to me either. I think I've covered that. I've beat it in the ground. We could run it again if you want to see the actual fusion takes place. I think that was a number 12, wasn't it? Here we go. What's the fusion? Not yet. Let's get ready to go. You see that little dotted line in there? It's sort of fusion. Bam. Photon. See, I gave that answer a while ago. I wanted to see if anybody remembered it was a photon, which is a form of... Okay. I'm testing you as well as myself. Okay, let's do one more. Let's do an LED fusion. It's a little trickier, you have to pay attention. Oh, I got it, I'm getting honest now. LED fusion technology. Here it is. If you want to remember anything from the night, remember this. An LED works on the principle of a recombination of holes and enhanced electrons. And that promotes an instantaneous energy release in the form of electromagnetic radiation. In this case, we talk in terms of photons. Wow. I think I've covered all those and thoroughly. It's time to get on with the fun stuff. Here's the fun stuff. I'd like to show you how I picture this in my own mind. It took me a while to get this. It's not perfectly clear, but it's not bad. It's good for an old-timer like me. Over here, I have an atom. It's made of gallium, arsenide, and phosphorus. In the center is a nucleus. If you take an electron away, it leaves a hole. Therefore, this atom does not have a net zero charge, it's plus 1p. There's a natural attraction between these two. That's just not a plain old-fashioned electron, that's an enhanced electron. Charge-wise, I'm going to tell it to go do its thing. Boy, it did it so quick, I want to see it again. I was blocking the view. Wow. Let's see that one more time, Bill. Are you ready? Here's this enhanced, what's it say? Additional minus charge is added to the electron by an external battery. Why is this LED, this laser LED working? There's a battery in this. Oh, the battery does the extra enhancement. Oh, okay. It provides this electron with additional charge, temporarily. Here I go. Here's the natural attraction of north, south, south, north. Here we go. I hit the wrong key. There, bam, wow. Wow, looks like I could slow that down. Let's see. Wow. This energy came out of here, electromagnetic field radiation, if you want to put the word field in there. And if this is happening like this over and over and over and over, picture this happening all the time, steady. The release of the excess energy is that field. The radiation is primarily in the form of photons over here. There they go, a stream of them, and they slam into some material. In this case, it could be phosphorus, for example. These photons excite atoms of a specific wavelength. Oh, I got it. The reason you can make a red one, a blue, and a green one is if you can set this up at the right frequency. If you can make this be the right frequency, and you've got something out here that is built out of that frequency. Think about that. We are stimulating the reds in an element to glow, to release photons, if you will. And they're doing it like a big click. Well, that's just fine, Bill. But how do they make these white LEDs that interest you so much that you decided you'd like to come to the fellows at Madison County and share your ignorance with them? And I am. Here we are. Number 15. By the way, notice it says only go to 26, and look what somebody stuck in this afternoon. Oh well, maybe we'll have time. Let's do a 15 and see a white LED. How do you make a white one? Oh, once again, something I couldn't show you a while ago, or didn't show you when I thought it should. I don't know why. There are no three elements. Gallium, phosphorus, whatever, arsenide, nitrogen. There are no three elements that will make white. On the various frequencies of the different colors, what frequency is white? A whole bunch of frequencies. So why did it take them 10 to 20 years to come up with what I am so proud to have right here? This one here is not too good, but there it is. Okay, it's a toy. By the way, you can buy these for $1 at the thrift stores. They're not out where you buy things. As you go through the checkout counter where they put that impulse buying stuff, look there and you'll see one hanging for $1. It's a great buy for $1, okay? You who gave the answer, if I have an extra one, you'll take yours home with you tonight. Okay, here we go. I'd like to do number 15. Do I have the 15 up there? Oh, I do. Here we go. Well, let's see what's different. Uh-oh, it's not gallium arsenide anymore. I'm going to use a diode that puts out light. It's not invisible light. Not invisible. It's non-visible to us, but it's not invisible. It's there, and if we had the right sensitivity, it's visible. We just can't see it. It's beyond our spectrum. Let's see. Outer ring of an indium gallium atom, nitrogen added. I said nitride here. With a vacant hole, one vacant hole with a plus charge. Here's my, enhanced electron due to a battery. Oh, this guy says I look like plus P, so I want to get an electron. You owe me an electron, pay up. So here I go. I'll sit down and get out of the way. I got this one slowed down. I didn't mean to cycle it that many times. Wow. That you may be going out the door. Well, this is still cycling. I don't know. Wow. Oh, come on. Stop for Bill, please. I'm going to break you. If I break you, I'm going to break you. You're going to keep going? That's because I held the key too long. I pressed the key down too long. If I just press it once, careful like this, it'll do it once. Watch. I told the truth. This is not stimulated. To make a white emitting LED, there is a phosphor out here. This photon that we can't see comes over here, a stream of IR photons, and bombards. They strike. They knock on the door with hard knuckles, and this phosphor glows. And it's not really white, it's whitish. If you look close at LEDs, white ones particularly, there's all kind of tints. Pale blue, pale green, even pinkish. They'll get it right someday, wait and see. All the words here are strictly the same words, basically. When you put the battery, depending how much battery you put on, depending how much you enhance this electron, that determines the brightness of the LED. Let's watch one more time before this happens. I'll try to, here we go. I'm ready. You'll see that there's the electron I couldn't accept right there. That electron comes out in this form, and it's scintillation, not stimulation. Scintillation is like a flickering, like throwing a match against the sidewalk and it pops bright and it goes out, sort of, It's that type of force. Now you know as much as I know about LEDs. Do I have anything else that might help you? I think so. The last time I'm going to do this one. Yeah, I saw that phosphor up there not glowing before it happened. Okay, let's see what number 16 brings to us tonight. See, you can tell what 16 is. Oh, I got it. If you use these base materials and you apply the right situation, you can make blue, green, yellow, and something, right? And, all right. Down here, if you do, IR, not applicable, you don't get a visible color. Here's the base. Here's some of the doping. They call this doping, if you will. The junction structure base of an LED. And let's take a look. Blue takes this many volts. If you had an LED at home and you were going to put a variable power supply to it, you turn on a half a volt and nothing happens. A volt, nothing happened. A volt and a half, nothing. 2 volts and still nothing happens. You got to get up around, that's what I'm talking about. What's it take to get a blue in the light? Look which works at the lowest voltage. Guess which LEDs we had first?
Red.
All kind of red ones. Would someone tell me what the time is? My wife gave me a signal. I've been here 2 days.
8:20.
I beg pardon?
8:20.
I can't hear you.
820.
820?
820?
Yes, sir.
How long, I better hurry, right, Patty? She says wind it up, okay. She's right. Okay, notice that IR, light takes this many volts. A white emitting LED, which is really an IR. Hey, look at the words, IR photons from this guy base causes a specific phosphor to glow, scintillate, not stimulated, white. And it takes about that many volts to turn it on, to make it. The one I demonstrate takes at least 3 volts. That's why you'll see usually 3 1.5 volt batteries, or 3 1.2s. 3 1.2s is 3.6, white LED ignites, if you will. And look at the, okay, that's enough of that. Okay, if you have a question, think about it. Here we go. Let's try number 17. I haven't done the 17, have I? At zero bias, a depletion zone separates the 2 regions. Oh, I got it. In this PN junction, if you don't have any voltage, the holes and electrons have either been recombined or been removed. But if you bias that PN junction on, if you turn the junction on by voltage, the LED will emit light. Oh, I got it. I picked a typical infrared, and there it is. It says you got to get up around 3 volts. But guess what? You don't want to go backwards, up around 5 or 10 volts. Are you ready for this? I can show you a circuit, show that better than me wording it. And you shouldn't solder there all day. If you got short leads, don't solder. I use a lot of short LEDs. Details later, maybe. Here we go. Short leads LEDs. Okay. Now let's try 18. We're just about out of here, except for I've saved the best to last, in my opinion. LEDs, typically the dome-shaped ones, are about half power points, are like plus or minus 30 degrees. Here's 0, plus 30, minus 30. And that's how the light, not much on the side. You know how they make an LED that you think it's got 180 degree light output, 360 output? Here's how they do it. Here's the dome guy, gives you like plus or minus 30. But here's something you may not have noticed. Some people do, some don't. They took the end of this plastic, picture if you will, a drill bit. You take a drill bit and you don't drill a hole, you just shave it like this. The point of this gray is right here. Pretend the green's not there. This gray line goes to here and comes back out here. You have a dimple inside the end of this. Here's the LED. Once again, it's a positive negative junction, a PN junction. That's the source. Here's how you put, okay. By the way, the long lead, the longest lead is what you want to put plus on. If you want to test, here we go. They sell them this way, one lead longer than the other on purpose. So when you solder them in, you don't have to unsolder them again unless you're careless. Here we go. This light comes in here and hits this angle. It hits this slope. Come on, Bill, I'm at the wrong angle here. It hits this slope, but you can only see part of the slope. Once it hits the slope, the light goes that way, and comes right up towards 360 of light. You ever notice that or not? Look at them. You can buy them. You can select the kind you want. This plastic end has an internal concave. Sometimes you actually curve them to get a parabolic action. There we go. Now, if you were all engineers, thank goodness you're not, because you'd throw me out by now. I would have shown you number 24. If you were, this has been the IRV with a lot of electronic type guys. By the way, I don't notice hardly any beards here tonight. There's one back there. I'm not picking on you. About 2. Anybody got beards over there? Anybody? Not too many. Okay, just goatee, maybe Mustang. How come engineers wear white shirts and how come engineers wear white shirts and a tie? They're afraid you'll find out they don't know anything. Here we go. This is, once again, this is N-type material. Remember? It's full of electrons. They're E and they're minus, and I show them as being like a marble. Who says they're that shape? Who says that electrons are round? They could be like gas, of vapor. They could be like dust. Who says that the holes are round? This is lots of holes, many holes available in this P material. P-type semiconductor. That should be darker. N-type semiconductor. Oh, I got it. This is the PN junction. But your title of this slide is Conduction, the Gap, and the Valence Band. Here's the conduction band, here's the valence band, and here's the gap band. This gap band is not physical. If you take, by the way, I'm going to try to con this fellow into something. P material, N material, I'm going to put them together. The junction is right here, right? Put your hands underneath. Careful, don't spill it now. Catch the junction, I'll sell you a pound real cheap. Engineers put the word junction in. There's no junction. It's a word we put there to describe nothing, okay? Think about it. we like to get a paycheck like everybody else. Hopefully we earn them from time to time. It's not a physical gap. It's often referred to as a forbidden band. Let's see. In semiconductors, atoms do not have tightly held electrons. Oh, and over here the P material doesn't have tightly held holes, but they're held because of the nucleus. At room temperature, if you don't heat this above room temperature, upon removal of any electron, a hole is said to remain with a plus charge. Take an electron away and it says you got a hole. And now I want to flow, oh, I got it. Hole flow would be this way, and electron flow would be that way. To make us look better to the rest of the world, we call this conventional current flow. Oh, electrons over here at room temperature seldom are ever promoted, given a prize, a free cruise trip to come over here. This guy, no conduction. Let's get going. By the way, that says page 0. Let me know what number that is when we finish this, and I better sit down so you can go home reasonably. How do we get this in material? We diffused in an N-type donor. Down here we diffused into this P material a P-type. Lots of electrons available, lots of holes available. This is a thin layer, this is a thick layer. Why? If I'm going to make an LED, and I'm going to have some light come out of here, I want the light not to be absorbed by this, you better keep this one thin, let this be thicker because it's going to make a little heat, and you better be able to stand the current as it has to pass. Oh, I got it. What you're showing here is an old-fashioned PN junction. There's the P, there's the N, and where they touch together, the gap band junction. And how big is that? Well, it's like a molecule. If you put these two materials together and press them together, it's very, very little spacing. The gap is really not much of a gap at all. I think we ought to learn, it says, what's this diffusion you talk about? I think I ought to hit the D key here tonight. Electrical charge diffusion. Here sits some P material, here sits some N material, and let's say the electrons and the holes are bunched like this. Why do they spread out like this? This young lady knows the answer over there. Charged polarities, plus and minus, like north and south. A like charge is repelled, unlike charges attract. These are all plus over here. Well, this plus wants to get away. These all want to repel. They want to spread themselves out. Same true over here. They want to spread themselves out because a like charge is oh, I got it. Crowding the junction, spread out throughout. All charges repelling. Diffusion is over. I'm glad that diffusion slide's over. Here we go. Number 1. Didn't count that one. I think we're all set. All set. Let's see. I think it's time to go on. I'm going to put a battery over here. And I'm going to connect it backwards. Look, I've got it highlighted. Number 2. I've got it highlighted. I'm going to reverse bias my PN junction. I'm going to put negative, positive, and positive. Okay. I'm not putting plus to plus and minus to minus. Okay. Guess what happens? I'm doing this till you say it out loud. I heard it. Thank you, folks. Thank you. Opposite attract. This plus says minuses, get away from the junction. This plus says, oh, get away. holes from the junction. This junction is starved. They pour this poor little junction, I draw it closer together, but it doesn't change physically. It's electrically it changes. And guess what? No hole flow, no electron flow. If you back bias an LED, it's not going to light without nearby or plus or minus charges. It's starved. Let's forward bias. Let's turn the battery over and put minus up here on the end and put plus down at this end. Uh-oh. And the lights do what? Oh, I got it. This minus, they repel each other. This plus says repel. Look at the junction. Look how it's being crowded. That junction says on one side I have electrons just dying to recombine with pluses. I just want to do that. I just want to do it so much. Bias voltage reduces the band gap. Not physically, that does not change side. Electrically it changes. That's the secret of PN junction. This is how your power supply diodes work. Here we go. If this was enhanced electrons, I'm going to show two minuses. That means it's more than one minus. That's how else can I show it pictorially? I have a 3-volt battery. I'm positive bias, I'm forward. I want to use an LED because I want to make light. Here I have these enhanced fellows, but I've learned, or you've listened to me say, that this hole will only take one minus. It won't take a double, it won't accept a fully charged enhanced electron. It won't accept it. But the junction is certainly populated now. Uh-oh, there's the magic words, prior to recombination. And once again, here's the symbols. I explained the symbols. Battery provides the necessary enhancement. Here we go. Watch what takes place. It's going to happen quick. There's what the atom would not accept. This material, this atom over here won't accept those minuses. Therefore, it's rejecting these excitation charges, that extra minus up here. Those are going to recombine. Holes accept only the level of charge of a non-enhanced electron. That's it. And if this is going to happen, hole flow will be this way, and minus is this way, and there it is. There's how you want to think of a diode. If this had a caret on it, I'd say a question over there. I'll take it later if you don't mind. I'm on page 5. I think I go to page 7. Anyway, picture an arrow. See that arrow? Pretend that arrow is pointing right here. That's the direction of hole flow, and when you see a schematic, that's what they're talking about. They stayed with that format. Here we are. Recombination hasn't taken place yet, but the whole enhanced electron recombination, the enhancement charge, is going to come up here. Here's those photons I've talked about. If you use the right material, this energy is going to stimulate, it's going to glow red, and you're going to see a very bright red light coming out. There'll be some out over here. I didn't have room to show it. There's red coming out. Some of the red doesn't get out. Some of the red is trapped in here and it doesn't get out. It stays in there forever. It's wasted, if you will. And here's what we're talking about. Whole electron recombo. Isn't it strange? We start with something that looks like this, charge-wise, but when it comes out, that charge has been used, and what's exiting is this fellow here. If you put a milliamp meter in here and a milliamp meter down here, I've even put the same meter here and then move it to here in a circuit, and I cannot get a difference. Maybe I don't have good enough equipment, enough sensitivity to measure the very weak currents, but I believe that's true. Here we go. These materials here, these elements, produce red at 460 micrometers, and it takes about 1.5 volts, 1.6 volts, and that's it. Number 6. Okay, the holes and electrons have recombined, and all is left was this minus. The atom won't accept it. That comes out as photons, radiation, and there it is. That's just a repeat. How do you make a white one now? How would you show chart number 8 and do a white one? Like this. Same story. The hole flow is this way. Electron flow is the opposite way. And what comes out over here are photons. Those asterisks represent my photons. And, well, that yellow relates to why did I put that yellow there? Oh, semiconductor, okay, the semiconductor gives you IR, okay, that's why I put that. Anyway, what happens is this is this non-visible energy, be it particle, be it frequency, you choose which. We call them photons, and they bombard this phosphor layer, which has to emit light. It glows, and it happens because of scintillation, and that's how an LED works. The white LED, decades later, just think, if our wits get sharp enough, we'll invent something else. There they are. The holes are going that way. The electrons are coming out this way. And I didn't show the symbol. I may have one somewhere else. I show the word diode there. That's it. We covered that and that. I don't think we want to cover that. That's easy. Let's do it. Let's do it. You'll get a degree tonight. Here we go. Probably your family at home will say, where have you been? Isotopes. This is tricky now. Isotopes occupy the same position in the periodic table. It says for every element, every doggone element in a periodic table, there can be isotopes for that element. They are identical in chemical behavior, distinguishable only in the atomic weight. Boy, you've got to have fancy equipment. You can't do this at home to measure that atomic weight. And all elements have isotopes. Not just all. And here's the symbol they use to talk about them. They use the form of A over Z, X. Well, what's the X stand for? Hydrogen, helium, whatever it is. The A is the number of protons and neutrons. You got to count protons and neutrons. And down below is the electrons, because the atomic number is the number of electrons. The quantity of protons and neutrons together, the total, over top of, divided by the atomic number, and then you write the letter. Oh, I got it. Here's one. Ordinary hydrogen is got one proton and one electron, and there's the symbol, H. Well, what if I happen to have hydrogen with an isotope? Let's pretend I've got a proton and a neutron. One, up here I got 1 and 1 make 2. I only still have one electron because that's its atomic number, and therefore you write 2 over 1 hydrogen, and you're signifying this. And guess what? They gave that a name. I hope it's here. Oh, good. They gave it a name. I wasn't positive. I say they. Deuterium. Deuterium. Is that how you would pronounce it? Deuterium?
Deuterium.
Well, let's look at over here. Here's plain old hydrogen. 1 proton, 1 electron. That's supposed to be on the outer ring. That's on in the inside, in the nucleus. But over here, I show in pale red. I wish it was brighter. I should do something else, or darker room perhaps. Anyway, I have 1, 2 over my 1 electron, and this guy is it acts different. It acts different. It really acts different. I thought you might like to learn about isotopes. Have you ever seen some food products? They'll say carbon 32, peanut butter 75. You know, I'm making this up. Anyway, those people that really work with this stuff and really know, have gone to school, they can play with those isotopes so you're blue in the face. You know what? There's always one more to be invented. The last one hasn't been made yet, in my opinion. Okay, so I've covered that and that and that and that. You don't start me on that one. How about solar path lights? Anybody have solar path lights?
Yeah.
I got 24. 12 that light up yellowish. That's called warm white. Have you seen how they cheat on white? They've got warm white, cool white, white, and bright white. I think they don't know how to pick a name. They need better marketing, in my opinion. Okay, so let's see if I can get away with it. What was it, a 25? Do I have that? No, I don't. Talking too much, Bill. It's getting dark out. There we go. On top of the solar light, if you will, the solar cell light, night light, if you will, is a SCA. SCA stands for solar cell array. You got to watch my shorthand. You have to look ahead of me. Metal cover, and there are the solar cells to get at least 3 volts, because that's what it takes to charge the battery. or at least 1.5 volts for sure. Okay, gotta have enough solar cell to get at least 1.5 volts, you'll see why. So there's the SCA. Sometimes they'll put a little, why am I hitting that button? Right here they'll put a little LDR, a light-dependent resistor. Think about this. Here is some solid state material, like an LED. And if you shine light on, the resistance changes. But it doesn't do anything. An LDR is worthless until you put some voltage on it, because then when the resistor changes, the current will change, and you can use the current change to ring doorbells, turn out lights, change headlights, etc., etc. So light-dependent resistors, LDR. Ohmage varies with intensity of light. Shine light on, down goes the ohms, not up. Down goes the resistance. Does the darkest senses? Guess what? It says, don't waste this, don't burn your LED in the daytime. Charge the batteries. Let's look at the circuitry quickly. Here's the circuitry. Here's the LDR. Here comes daylight. It says, charge my little NiCad and keep it at a full 1.5 volts. You can get these up to 1.3 if you really slam them. So here's 1.3, or at least 1.25. Here's this LDR. And it says, I will change my resistance and I will turn on this 20 kilohertz oscillator. 20,000 times a second, a square wave oscillator. Click, 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 click. I gotta, here we go. They'll take that voltage and bring it down to a little tiny ferrite, powdered iron that doesn't touch, the molecules don't touch each other, they're insulated, if you will. Insulated iron, ferrite, toroid. That's a transformer, and that will step this voltage up, this AC voltage, it will step it up and make it so it goes to the light-emitting diode. Because this fellow needs 3 volts for a white, this is a white, for photons coming out. During the day, the SCR charges the battery. At night, the oscillator transformer, it's a little switching power supply is what it amounts to. A little switching power supply steps up the LED voltage. The oscillator is a 4-lead, a little tiny plastic IC. It's not even a good quiet, it's a little, they just put like a black dot of paint over it to keep humidity away from it. If you haven't torn one apart, you should. They're fun. Anyway, here we go. You have this 1.25 volts to start with. There it is. That's the average DC voltage you have coming over. They take that average voltage, and on top of it, they add this voltage, and they only add it for half the time. They don't keep it up here all the time. If this time here represents 20 kilohertz, that time, 1 over that quantity, turns out, there it is, 50. Look at that, 50 microseconds, 50 microseconds. Half cycle will be 25, 25. Half the time, you've got 3-point bolts running on this LED. 50% of the time it's under pico, but it averages out about 3. That will be cause the current to flow through the LED, but it's only on 50% of the time. The LED is a phosphor. That phosphor takes time to glow. The phosphor doesn't come on suddenly like over here. It takes time for that phosphor to get up to glow. Then you take away the photons, and it takes time for it to quit glowing. Because of that, this 20 kc blink rate, your eye wouldn't detect it in the first place, but the photocell says, pardon the expression, I'm fat, dumb, and happy. I say that to my best friends. So be it. Okay, I think that covers that pretty well. I think I got one more. Yeah, I hit the wrong key. Yep, here's how they sell them. There's warm white and soft white and cool white. In my book, I thought white was white. These look yellow. That's why I used that color. They look really yellow. They look very yellow. These look less yellow. These are more whitish, and they're bright 4,300 Kelvin degrees. Kelvin. So if you buy these, you're buying yellow light bulbs for your house. If you know, we lived on this planet a long time. Our eyes are taught to like sunlight. It's built into us. Long time. But in my house, I spent $250, and I'd have a lot of LED white bulb. Some cool white. I even have a daylight or two. If you visit my basement, you'll see what I'm talking about. In luminescence, over here is 50 lumens, okay? So if you, dim is over here about 1, 2, 3, 4. 50 is considered average for, and bright is somewhere above 100, okay? I brought some lights with me tonight, and I'll show these as quickly as I know how. Here's one. This used to be a toy, in my opinion. I got it. And there's one. That's called, that's longer back. Here's the other one, right? And, all right. And it has this mode here. If you're a true fisherman and you want to let this on all night, and you just want to see it'll bait your hook and not attract another wolf or something, you can buy them with blue or yellow. By the way, all LEDs. This product wasn't on the market, okay? Do not buy one of these. It has 65 LEDs in one end. It's obsolete. I won't shine it directly in your eyes, but if you just look here, you'll see it's got just some part of 30 of them lit. But if I go to the other mode, all 65 are lit now, okay? I won't, okay. Why buy one of these when you can buy the same thing with one single LED? It does the same job, same brightness, if not more. I'd like to show you one of those brighter lights if I have one here. And I don't see one right here, probably in this other patch. Here's one that you use yourself. Oh, this noise over here. Here's one you can buy from Tractor Supply. Is that a good name, Tractor Supply? Yeah. I got this for $9.99, and I won't point this one right at you, but it does put out, pretty good light. Okay. Here's one. A friend of mine who lives near Atlanta gave me this as a present, and I thanked him my own way. Anyway, so I'm going to try to demonstrate this one if I can. Oh, hey, this is pretty good, isn't it? That's all right. Well, I wonder how it would work over that wall. Oh, suppose I really want to see that flag over there. Wouldn't it be nice if I could do this? You can actually see the segments in the LED it's inside. There's a single LED here, okay? Okay. Something like this, if you look around Costco, he purchases Costco in Atlanta. I went to Costco in Columbus, they didn't have this item, and I don't know why. About $20, 19 something he paid for it. And you can take these LEDs and this young lady over here, she's really helped me out a lot tonight. If I gave you a box of flashlights, would you pass one out to each fellow? Yeah. I'll be right over. Leave one cover will light. Yes, that's it. That's not the one I want. Here's the one I want. Here's one that has an incandescent bulb inside. Boy, that's not much of a light, is it? Here's one with some LEDs. All novelties. Of course, these are designed to be taken out of a holder and walked away with somewhere from a wall. To me, there are so many novelty products, and the manufacturers are trying to get all their money back for the product right now. The price is way overpriced, in my opinion. One of our sons gave this to me. I guess he thinks I need this. I don't know why, but anyway.